Hello everyone, my name is Bijan Taslimi, and today I'm presenting our submission to the 2020 RAS problem solving competition. It's a mixed integer programming model for freight train travel time estimation by minimizing delay of trains. Here is the list of authors. It's me, Farnaz Babaie, and Dr. Hongcheng from University of Florida. We first have an introduction to this problem, then you have a problem description. Next, we'll illustrate our mathematical model, and then we take a look at some computational experiments and numerical results, and finally, we'll have a conclusion. Railway management has become extremely challenging in the recent years. There are many problems arising in this field. Train timetabling or scheduling is a crucial problem in this field. In this problem, we want to determine departure and arrival of trains at each station through their path. There are various operational constraints that need to be considered in this model, as well as network structure that should be imposed into the model. Of course, train delays can occur and they can affect the planned timetable dramatically. So travel time estimation has become an interesting problem in this field. There are three main categories of the methods utilized for this problem. The first category is optimization methods, in which we are finding an optimal train timetable. The second category is simulation models, in which we build a simulation model to analyze the behavior of system. And finally, there are data-driven models in which we apply statistical and machine learning methods to estimate the travel time. In this challenge, we were asked to use an optimization method for this problem. Our goal is to estimate travel time of trains by determining arrival and departure time of them. The followings are given in this problem. First, network characteristics such as stations, tracks, and connection between stations. We also have business constraints in this model that will be discussed in the next slide. There are also resource availabilities such as number of yard tracks and number of siding tracks. We are also given a planned train schedule in this problem, and we are also given some source of delays. Now let's take a look at business constraints. Three types of delays are considered in this problem that can occur due to unavailability of resources at yard, or crew, or locomotive at the origin station. In this network, there are single tracks, double track, and 4-track sections. And we also have siding and overtake activities in this problem. We have low priority and high priority trains, where we expect high priority trains to have a smaller amount of delay, so they can overtake low priority trains in order to decrease the amount of delay. And we should also consider the impact of delay of a train on the schedule of other trains. There are important assumptions considered in this problem. First, yard tracks can be utilized for siding as well as siding tracks. There is a 5-minute penalty delay for siding. We can have pick-up or drop-off activity at a non-yard station, and it occurs at a separate industrial spur. So the train doesn't occupy any siding or mainline track. At intermediate stations, we can have an early arrival and early departure, but at stop stations, we may have early arrival, but we cannot have an early departure. And finally, in this problem, the distribution of delays is assumed to be log normal. And in our model, we assume that all trains have a delay equal to the mean of the corresponding distribution. Here is a list of notation and parameters used in our model. This is just for your reference. Here we have the list of sets we defined, and here is a list of parameters. Now we look at decision variables. Variables x and y are defined for arrival and departure time. These are continuous variables. Decision variables delta positive and delta negative are defined to consider positive and negative delay of trains at each station. By positive delay, we mean when a train arrival is after planned arrival, and a negative delay occurs when a train has an early arrival. Binary variables P, Q, and R are defined to determine the order of departure and arrival of trains at each station. We also have variables Z and H that are defined to be utilized in the siting constraints. And finally, variables W are defined to determine that which track is utilized by a train on a 4-track section. Now we have our constraints. We first have departure and arrival time constraint. With this constraint, we impose yard, crew, and locomotive delays, as well as the siding penalty, stop duration, and travel time between 2 consecutive stations. We next have delay calculation constraint. And then we have arrival and departure order constraint, because for each pair of trains passing through a particular station, it is necessary to specify the arrival and departure order. We next have siding and overtake constraints. Constraints to determine whether a train has a siding at a particular station or not. Besides, we ensure that the siding capacity is respected. Then we have single track capacity constraint, which impose the capacity of the single tracks in the model, because we know on a single track, at most one train can move at any time. Here is the set of constraints to impose double track capacity, because on a double track section, we know that at most 2 trains going in opposite directions can move at any time. And similarly, we have some constraints to impose 4-track section capacity. And finally, the following constraints are for dropping off or picking up a capacity at non-yard station, because they ensure that at most one train can have drop-off or picking up activity at the non-yard station at any time. Besides, it makes sure that any siding track or mainline track there. And here is our objective function. This objective function is minimizing the total penalized delay at the stop stations and final destination of trains. We considered a penalty coefficient of lambda for high priority delays. This lambda is greater than 1. And with this way, we can impose the importance of these trains in our model. Now, let's take a look at our computational results. Here is our test instance that we were given in this challenge. It was a network with 61 stations. Some of them are single track, some of the sections are double, and some of the sections are 4-track sections. This is a simplified version of the network shown in this picture. We are also given a planned schedule for the trains for 2 consecutive days. We coded our model in Julia programming language, and we solved it by Groovy on a laptop computer with 8 GB RAM. We also set our MIP gap to be equal to 1% to terminate the solver once a desirable solution is found. We also utilized a lazy constraint option in our model, and we considered constraints related to siding and yard activity and non-yard stations to be lazy, and it significantly improved our runtime. This table shows our numerical results for each day. The second column of the table contains the number of trains in each day. The next 2 columns contain the number of continuous variables and binary variables. We see that we have more than 1 million binary variables for each model. The next 2 columns show the total number of constraints and the number of lazy constraints in the problem. And we can see that we have more than 2 million constraints in each case. And the next column shows the runtime of the model. And finally, the last column shows the MIP gap obtained at the termination. We can see that our model can be solved very efficiently, even though it's a very big model with many binary variables and many constraints. So we can obtain near optimal solutions efficiently, which shows the superiority of our model. Let's now take a look at some outputs of the model. Here is a train timetable for one of the routes in the first day. We just picked some trains randomly to show the movement of them through the route. And this figure shows the number of sidings that occur at each station that has a siding or yard track for day 1. So we can see this station EHV has the most number of sidings, and it was not surprising because it's almost in the middle of the network and many trains pass through that. This figure shows the percentage of trains that have different number of sidings through their path. It's for both high and low priority trains. We observe that more than 70% of the high priority trains do not experience any siding, which shows that our penalty coefficient that we consider in the objective function is working very well, because they overtake low priority trains and pass them, and they do not have any siding in most cases. And we observe that almost 60% of the low priority trains at least experience 1 or 2 siding. And here, this figure shows the total amount of delay for some of trains versus the amount of delay caused by resource unavailability or mandatory stop at stop stations. So we observe that more than 80% of the total delay is caused by unavailability of resource or mandatory stop, which shows that, which implies on the importance of having an accurate estimate of the delays to determine a high accuracy travel time estimation. Now, let's take a look at the summary and future study. We observed that our optimization approach enabled us to consider all restrictions in this model, and we were able to perfectly formulate it. We also evaluated our model by implementing it on the test instance provided in this challenge. And we observed that this approach was quite efficient, and we could solve the model very efficiently to obtain near optimal solutions in a reasonable amount of time. And for future study, we have some suggestions. The first one is that we can consider a variable amount of delays that depend on the trains, stations, or the time of the day, because we know different trains or different stations can experience a different amount of delay. And also, we could consider other sources of delays, such as weather conditions or planned or emergency maintenance that occur in the network. And here is the list of references we used in our study. Thank you.